Okay, let's get started. I'll open us in prayer. Father, thank you for this evening. Thank you for the topic we're going to study tonight. Even though it might challenge our faith, Father, to a degree, Father, we trust in you and we trust in your word. And so, Father, give me the right words to say this evening, words that will glorify you. We ask this for all our church tonight. In Jesus' name, amen. Amen. All right. I kind of hesitated in that prayer because this is a tough topic tonight, this starlight and time. I'll try to make it fun. And it'll be a little bit easier to understand maybe if I've got some good slides and make it fun. But, you know, we've looked at evolution versus special creation. And I dare say we've walked away feeling pretty confident about that subject, that, you know, we've got the evidence that indeed special creation is the way God did it. And so that pretty much buoys your faith when you feel like that. And then on the age of the earth issue, the first night we looked at evidence that really shows that the earth is young, at least the evidences that we looked at. Certainly much younger than 4.5 billion years. And then last week we examined the reasons that would explain the wrong answers given when you use radiometric dating, why they would get answers in the billions of years, or for the carbon-14, why they would get answers in the 25,000 year range and so forth, and why, because they haven't considered the flood, or because they haven't considered the rate of decay perhaps might have changed over the past, why their answers may be wrong. And we even saw evidences where there's good reasons to think that that the evidence actually points to a young Earth even in those cases. But tonight I'm going to make your head hurt a little bit on this starlight and time. At least it made my head hurt, and we need to grapple with this one. Usually this topic is skipped in creation science courses, unless you're getting a creation science course from somebody that believes in billions of years. But for a young Earth creationist, this topic usually is either kind of passed over, you know, let's don't mention this one, or we don't know about this one, and so forth. But we need to deal with it. It's just like, you know, we just study the whole counsel of God. We don't skip over the verses that give us a problem. We don't skip over the evidences in the universe that give us a problem either. We kind of, because God told us to subdue the earth and to look into things, and so we're going to look at that tonight. Relativity, time dilation, white hole cosmology. Have I given you a headache yet? Those are kind of the topics we're going to be looking in tonight. Let me ask you a question. This is not necessarily a test, but see if you can get this answer right. How long is a light year? Well, don't read the book. Just tell me, what's your definition? What is a light year? How long is a light year? I didn't. Yeah, distance light travels in a year. And so the key word there is distance. Light year is a measurement of distance. It's not a measurement of time. There is a time element to it because it's 1 year. So when you say how long is a light year, it's about 6 trillion miles. That's the distance that light would travel in a year's period of time, 186,000 miles per second. And so you multiply that out by how many seconds in the year, and that's about 6 trillion miles. So a light year is a very long measurement of distance. And so, let me get my... 6 trillion miles. Now, so when we go out tonight and we see a galaxy, perhaps the Andromeda galaxy, actually that would be in the summertime, but you see a galaxy that's supposed to be 2 million light years away, how long of those... Now, you understand when you're looking at starlight, you're looking at photons. These photons have left that galaxy, and they're now reaching our eyes this evening when we go out and look at it tonight. And so let me ask the question. For a galaxy that's supposed to be 2 million light years away, how long ago did those photons leave that galaxy? Yeah, that's right. So there, in that case, even though light year is a measurement of distance, it's telling us something about time as well, because time is an element of that. So if it was 2 million light years away, then that means that that light has been traveling for 2 million years, the photons that are reaching our eyes tonight. All right, honest question. Does that bother you? A little bit. I mean, you think, I mean, if the Earth and the universe are 6,000 years old, you're thinking, okay, 2 million years ago, but it's only 6,000 years old, something's got to give here. I've got to be able to explain that. So, matter of fact, this is a question that many people struggle with. It's, matter of fact, how I got started teaching creation science. I was having lunch with David Powell. You remember David Powell? And I was telling him about a book I was reading. Matter of fact, I've got a copy of that book here. It's called Starlight in Time. And he said, "Oh, why don't you explain it to me?" I thought we were just having a luncheon conversation, but he was baiting me to find out whether I was able to teach a creation science course. And so evidently I sufficiently explained it to him. But this is that book, Starlight in Time. It's by Russell Humphreys. And it was written 10 years or so ago. 1994 was the first printing, so it's been out for a while. But that's how I got started teaching this course about 8 years ago. And your mind immediately starts to try to reconcile this. Well, perhaps the speed of light has changed in the past, or perhaps God just put them all out there in a short period of time and strung all those photons out. We'll look at those different theories. But let's take a look at the reasonableness of this assumption, whether the universe is that big. This is what's known as a Hubble deep field view out of the Hubble Space Telescope. And you look at this picture and you think, okay, that's a pretty picture of different stars and so forth out there. But let me show you the stars in this picture. Those are the only 3 stars in that whole picture. What do you think the rest of those things are? Yeah. Is that what you were going to say? Good man. Galaxies, exactly. And you can, when you look at the close up at them, you can see that's kind of a little spiral right there, and here's a little spiral. You can almost see the spiral arms in this one, and they're kind of elongated, and so that would kind of give you an idea of a galaxy on its edge, looking at it as sort of an edge view. And so there are tons of galaxies out there. And this view is the deepest view that you can look at of the Hubble Space Telescope. It's the farthest the Hubble Space Telescope has actually focused out there. And when they took this picture, this is a long exposure picture, okay? 10 days. They opened up the shutter on that camera on the Hubble Space Telescope and left it open for 10 days. Now, actually, they turned it off, on and off, because you have to go, around, but, for so many hours a day, they keep turning it on until they had collected light equivalent of 10 days of light. Because when you just look out there with the telescope for just an hour or so, all you see is inky blackness. But as you continue to focus and the light continues to collect, and for 10 days, you get this picture right here. You see some of the light has different colors, blues and reds and whites in that picture from those different galaxies. And these galaxies are supposed to be somewhere in the neighborhood of 12 to 14 billion light years away. That's a long, long way away. And so are they, of course, if you see a picture of me when I was 5 years old, and I tell you that picture was taken 50 years ago, you're going to know 2 things about me, right? One, I was very cute back then. And the other is, how old am I? 55 years old, exactly. And so you can tell a lot about something by that. And of course, the question we're going to ask about these galaxies is, are they really that far away? Are they really that old? And I'm going to have to answer yes for a number of very commonsensical reasons, okay? And we'll look at what those reasons are. So, how do they know how far they are? Well, there's several different techniques they use to measure the distance of a star or the distance of a galaxy. For nearby stars, this is the technique they use. And it's called the parsec measurement, where the sun is here and the Earth in June is up on this side of the sun, and in December, 6 months later, it's over on this side of the sun. And as you look at a near foreground star, this little red star right in the middle, against the background of stars that are very, very far distant, you're going to see that in June, this star looks like it's sitting over here just to the left of this way distant red star and blue star out here. But when you look at the same star again in December, its background is going to change, and it looks like it's over here next to this yellow star, okay? So the background shifted. So the star appears to move in the sky, you know, backwards and forwards, okay? So that, and the closer it would be, the more it would move. The further away it is, the less it moves. And so that makes sense. And there's actually basic trigonometry. You can take the measurement of this angle right here that it subtends between that, and there's a direct formula, a very simple formula that says this is how far that star away is. And that, like I said, that works up to about 30,000 light years away in that. Now, that's a big triangle, you know, 186, well, it's 93 million miles to the sun, right? And so this would be 186,000 miles across the base of that triangle. So you can make a pretty big triangle right here to do that. When you look at a galaxy, that's a different sort of measurement because the galaxy is so small, so far out there, and it's so far out that the background stars don't change in relationship. I mean, it looks the same in June as it does in December. And so when you look at this galaxy out there, you may see a galaxy that in your telescope you can measure how far across your field of vision in an eyepiece of the telescope it would be. And then if you see a further distant galaxy, what is it going to look like? Well, it'll be smaller, okay? So the further away it is, the smaller of the angle that it's going to subtend in your field of vision for a given eyepiece in your telescope, given the magnification power of a telescope. And so that's a very common sense technique. Now, assuming that these two galaxies, one that's real tiny in your field of vision, the one that's much bigger in your field of vision, assuming those two galaxies are the same size, which is, I mean, they won't be exactly the same size, but a galaxy is a galaxy, and all galaxies have somewhere in the neighborhood of 100 billion stars in them, and they're about 100 billion light years across in terms of width. And so you can get close by making that assumption on these galaxies. And so that's how they measure these far distant galaxies, is by using that kind of technique. You can see even those galaxies that in that Hubble Space Deep Field View, I mean, you can even measure, you know, how wide that galaxy is, even though it's a very tiny field of view. You can measure those things because you can actually see the structure in those galaxies. They're not like pinpoints of light when they're that far away because they're so massive and so big. So that's another way. There's a third way, and that's just by the brightness. I mean, given, they call this candle power. The closer a light burning object is to you, the brighter it is, and it changes by the inverse square of the distance. In other words, twice as far away would be 1/4 the brightness, okay? And let's see, what's the other? If it's 9 times brighter, then it's 3 times closer, because 3 times 3 is 9, so square the distance right there. And then finally, there's another common sense one. I mean, you can just kind of do the back of the napkin approach on this one. Looking through the Hubble Space Telescope, we can count about how many galaxies and about how many stars are out there. Matter of fact, there's a catalog of all the stars that they observe, computerized catalog, and so they know about how many stars they are. And they know about relatively how far away they are to each other. If you took all those stars and you compressed them down and crammed them into a single sphere that's about 6,000 light years across, because that would explain 6,000 years of creation as far as the light coming from those galaxies and stars, then there would be about 3 stars in our own solar system. It'd be that crowded. And so it just really doesn't make sense with that. So you might ask the question, why would God make the universe so big? Well, I think we went over this verse a week or two ago. It was to show us how big his thoughts are, how much bigger his ways are than our ways. Isaiah 55:8-9 says, "For my thoughts are not your thoughts, nor are your ways my ways, says the Lord. For as the heavens are higher than the earth, so are my ways higher than your ways, and my thoughts than your thoughts. And so Psalm 115:16 also says, even the heavens are the Lord's, but the earth he has given to the children of men. And so that's God's domain out there. Now, he's letting us look at it, but we don't know how he did all that. And so this is the mystery of the heavens out there. So we could leave it at that and say there's some tension in this, and we'll just let God be God, and that's a good way to be, okay? But we're gonna dig a little bit deeper and see if we can't glean some things by just looking at what we do know out there. Up until a few years ago, creation scientists had only two theories. Up until this book came out, maybe about 10 years ago, there was two theories, and the one theory was the mature creation theory. Now, this is the theory that God can create things with the appearance of age, right? I mean, he made Adam. How old was Adam when God created him? 30 years old? I don't know. He wasn't a baby, but he was a grown man probably. And, I doubt if he had any cavities in his teeth. He probably didn't have any ill health problems or anything like that. Didn't have any wrinkles on his brow or forehead or anything like that. He had nice smooth skin and so forth. But I asked you this question a few weeks ago. Did he have a belly button? I don't know. He looked funny without one, so perhaps he did. But and did trees, when God made the trees, did they have rings on those trees? I don't know, but I suspect they did. It's part of the structure of the tree and so forth. So God can create with the appearance of age. And when Jesus made fed the 5,000 and made the fish and loaves, duplicate and so forth, he had to make that bread baked, okay? It had to be cooked. So he can create with the appearance of age. No problem with that. But there's a problem, because in the sky we see things happening. We see events happening up in the sky with our telescopes. We see things like supernovas, explosions of stars and so forth. As a matter of fact, back in 1987, there was a supernova. Matter of fact, the number of that supernova is 1987A. That's when it happened. And this is a star that exploded over a 2-month period of time. We can actually observe the explosion. And it was, or is supposed to be about 160,000 light years away. Now, immediately, that gives you a problem, because if it's only 6,000 years old and it's been traveling for 160,000 years, then how do you reconcile those two? But what they saw was this flash of light. So here's this star. Somebody's out there observing this star, and all of a sudden, he sees it explode like this, okay? And maybe that happened over a 2-month period of time or something like that. And then as the years passed, from 1987, you could observe this expanding gas cloud. They call that a light echo or something like that. You could see these rings appear where the star used to be. The star is no longer there, but you could see this explosion. And so, if these events never actually happened, because maybe God did it by the mature creation theory, he just put those strings of photons out there for us to observe this, but since it's supposed to have happened more than 6,000 years ago, it didn't really happen, then it'd be kind of like watching a fictional TV show, right? It's not right. And so here's the explanation of how that works. All right, so this is Adam's eyeball right here. He's looking out at the universe here, and he sees a star, okay? And so Adam and all his children continue to see this star over the years. It's the same star that we saw back in 1987. And so as time passes, and God would have strung out these little photons, okay? Because the photons, God could string them out like a bead of pearls, and so as you're looking at the star, you're seeing photons that have been traveling for 6,000 years, since Adam. But the ones further than that, God had to just kind of string out there. And so God put the star and all the photons in place so that Adam could see the star the first day. Didn't have to travel for 160,000 or 10,000 light years ago like this. And so as time moves on, we continue to see these photons, and then, in 1987, we see the explosion. And so here we are looking at this little star down here, and we see the supernova, and boom, a few years later, we see this first ring here. And so now, instead of a single strand of photons coming from a single point of light, which would be the star, now we have a kind of a circular string of photons. That would be the first inner circle. And then these photons have been created in transit by God, according to this material creation theory. And so God would have to have these photons that haven't arrived to the Earth yet hit the Earth about the time, that the next few years pass, and then a few more years pass, and we have another ring. And a few more, because remember, this event didn't really happen because it's 160,000 light years away here, and so finally this would be where the photons end up here. So this is what we're seeing with this exploding supernova out here, and so here's all these little photons created in situ by God at the creation event 6,000 years ago, but He's got them strung out all the way to 160,000 light years away. Okay, so if the heavens declare the glory of God, Psalm 19, the heavens declare the glory of God, skies proclaim the work of His hands, day after day they pour forth speech, night after night they display knowledge, there is no speech or language where their voice is not heard, right? Wonderful verse. So the heavens declare the glory of God, but if the heavens are actually largely fictional, what does that say about God's glory? So I don't know, I wouldn't push that too hard, because perhaps it's a good fallback theory, but I'm not really satisfied with this mature creation theory. All right, the second theory that creation scientists came up with was something called the C decay theory. Now, what does C stand for? Anybody know? It's a C means the speed of light. Yeah. So E equals mc squared. That's energy equals mass times the square of the speed of light. That was Einstein's equation. So C would be the speed of light decay. So speed of light decay theory, or C decay theory. So, which says that the speed of light used to be much faster than it is today, and perhaps that explains how the speed, how these light from these distant galaxies and so forth could have reached to here, because they were traveling. Those photons were traveling much faster 6,000 years ago than they are today. Now, Barry Setterfield and Trevor Norman wrote a paper on this a number of years back, and what they did was they studied the history of people trying to measure the speed of light over the past 300 years. Believe it or not, they have been trying to measure the speed of light for 300 years. Now, you can expect that their measurements 300 years ago would be very crude because their instruments were very crude. But they studied the books and so forth, and they were able to kind of interpolate some of that data, and they charted it, and they came up with a chart that, if you look at the curve over the last 300 years about what the speed of light has been, then if you keep extending that curve on out, it would have been considerably faster back 6,000 years ago if you just interpolate that curve out there. And so this was their theory, and they say, well, here's the data that proves that. But anytime you do a statistical analysis of data, you've got to throw what they call the outliers out, the anomalies, the numbers that don't make any sense, because you want them to fit a curve, but if they're way outside the normal range of values, then you throw those numbers out and you use the rest of them, okay? Those are the outliers. Well, once you throw the outliers out of his data, the trend goes away. He needs those outliers in order for his trend to show up. And so the data is not so good from a true statistical perspective. And the other problem with the speed of light decay theory, or the C decay theory, is the speed of light constant is enmeshed in all the fundamental physical equations, the laws of physics and so forth that we've observed. Not that we've discovered. Well, we've discovered them. We didn't invent them. We just observed how God's physical equations and forces work. And so this speed of light constant is enmeshed in all of these fundamental formulas. And so if it's much faster, it really changes the way the whole world works. And so that's another problem with the speed of light decay theory. Now, I will say this, that a gentleman by the name of João Magueiro, who is from Portugal, he's a scientist from Portugal, wrote a paper. He's a member of the Royal Society of London, which is an astronomical physical society, a brilliant man. But he's challenging Einstein's idea that the speed of light is a constant, independent of relative velocity of the observer. And he's saying that the speed of light must have been an order of 70 magnitudes faster earlier on. And so, it's even the secular scientists are starting to having to answer to some of the papers, some of the works that he's done in looking at this, because what he discovered really solves a lot of the phenomenon that they can't explain. Okay, I don't have time to go into that, but just suffice it to say that there is some effort being done that could kind of resurrect that C decay idea. So I don't want to completely dismiss it, but another point is there's really nothing in the Bible that even hints of either the mature creation theory as far as the light and time and so forth, or this C decay theory. And so I think we really need to look a little further, at least entertain some other ideas as well. But before we go into this theory that I want to present to you this evening that came from this book, Starlight and Time, I need to kind of set the stage a little bit, because we need to look at what the Big Bang's all about. We need to look at how they have this idea of a expanding universe. By the way, how did they conclude that there was a Big Bang 14 billion years ago or whatever? What's the premise? I mean, it used to be that the steady state theory was the accepted theory, that the universe has always been here, and that there was no beginning. And they liked it like that, because if there's no beginning, you don't need somebody to get it started, right? The Big Bang does imply that there is a beginner, right? And so that's the good news about the Big Bang from a Christian perspective, is that if there's a beginning, there must be a beginner. And so, but that's about all the good news that you're going to get out of the Big Bang from a Christian's perspective, because of it really supports evolution and all those other things. It's because the way they concluded that it was a Big Bang is because they observed that the universe is expanding, an expanding universe. The way they discovered this was something called the red shift. When you observe distant stars and distant galaxies, you can plot out the frequency spectrum of the light that you're observing. Some of them, when you put a light through a prism, it splits it up into different colors, right? You've seen a prism work, and you can get the different colors and so forth. Every light has a signature to it. The fluorescent light has a certain temperature coming out of it. The sun has a different temperature coming out of it. As far as the type of light, some light's yellow, some light's red, some light's blue. Well, when you look at these galaxies, these distant galaxies, you notice that the further away galaxies are distinctly shifted to the red side of the spectrum, okay? And so they assume from that the galaxies are flying away from us at some pretty incredible speed here because of the amount of the red shift. And the further away they are, the faster they're moving away from us. And so I'm not going to take the time to try to explain how that works, but suffice to say that that's a pretty good evidence that the that the universe is expanding right there. There's some problems with it also that they need to kind of sort out. I'll explain those to you. There's this something called discordant redshifts. There's some anomalies out there in the data. The Andromeda galaxy, by the way, is blue shifted. It's not red shifted. So here's a galaxy that's unlike all the other ones. It's actually coming toward us instead of flying away from us. If a blue shift means it's moving like that. And somebody else, Halton Arp, did some studies on the amount of the shift between these different galaxies, and what he's come up with is the idea that the shifts are quantized. In other words, for galaxies in a given region, they all seem to fall into a very narrow range of shift amount. And then the further out galaxies skip all the rest of the ranges in between there, and then they fall into a specific range. So you get this clumping of this is the amount of red shift. If you draw a plot on, here's the least amount of red shift, here's the most amount of red shift. If they weren't quantized, you'd expect them to be kind of evenly distributed all the way out. Except what they see, though, is that this group is clumped up around this amount, and then you skip a bunch of spaces, and then it's clumped up around this amount for the next group, and then this amount, and so forth. So you get these, they call it quantized redshifts, and there's something going on there that they can't explain. It may blow the Big Bang out of the water if they really figure out what that means, but that's something they're going to have to do. I throw that out there just to say that the Big Bang is not a perfect theory. It's got some problems too. Next thing I need to explain to you is this idea of the cosmological principle. It's also known as the Copernican principle. It's a concept that says it looks like we are at the center of the universe, but we're really not in any particular place special. Now, what I mean when I say that. When we look out at the sky, if we look this way, we see stars as far as we can see, galaxies as far as we can see. If we look that way, we see stars as far as we can see, galaxies as far as we can see. Now, no matter where we look, we see stars and galaxies as far as we can see. Now, if we were at the center of the universe, that would be evidence for that, right? Because if you're on the edge, you'd look at one way, you'd see inky blackness out this direction where you're close to the edge, and the rest of it would be, on the other side would be stars and galaxies as far as you can see. That's not what we observe. Now, scientists don't like us to be anything special because we're created by random chance, right? And so they don't want us to be at the center of the universe. So I have to think about this and kind of come up with a different explanation here. So here's the explanation. Hawking, you've heard of Stephen Hawking. He's the one that's in the wheelchair, that has to speak with a computer and so forth. Brilliant man. Anyway, they wrote a book called Large Scale Structure of Space-Time. And in that book, here's one of the statements they make. It says, "We would not claim our position in space is specially distinguished in any way. We shall call this assumption the Copernican principle, implying that the universe is approximately spatially homogeneous." Now, approximately spatially homogeneous, I think that's a fancy term for meaning that it's just the same everywhere. It's just homogeneous out there. In other words, no matter where you look, you're going to see the same thing. Matter of fact, if you moved, 1 billion light years in that direction, you're going to see the same thing as if you were right here, as far as stars everywhere and galaxies as far as you can see. You couldn't get to an edge because there is no center or edge. Now, one way to explain that would be to say that the universe is infinite. In other words, travel off this direction in a spaceship, as far as you can go, you're still going to see stars and galaxies, right? That would be an infinite universe. They don't believe in an infinite universe anymore. So they've got to come up with another way to explain the fact that there is no center and no edge to the universe. Now, here's one writer's attempt to explain this. This is out of the Science and Engineering Research Council from the Royal Greenwich Observatory. He writes, "One of the hardest concepts to accept is that the universe is everything that is. Not only the matter and energy, but all the dimensions as well. There is no outside to the universe, and it has no edge, at least not in the usual sense that we think of these concepts." Continuing on. "When we think of the Big Bang, we instinctively think of the small universe expanding like a sphere into empty space or empty void. Unfortunately, this is incorrect. The dimensions that we commonly use, 3 spatial and 1 time, are all mixed up when the early universe is concerned, and normal concepts of space and time are not valid." He continues, he says, "The only way that it can be partly understood is to consider the 2-dimensional analog of the surface of a balloon which is being inflated. The surface is everywhere continuous, has no edge, and yet is expanding. The 3-dimensional analog, whose understanding defeats this writer, will represent the universe." And so you see the surface of a balloon, and you could have galaxies on the, stars and so forth on that surface of the balloon, and you start blowing it up, and it gets bigger. Now, if you're walking on the surface of that balloon, you could just keep walking forever, and you'd never hit the edge of it, right? And so that's 2-dimensional, okay? 3-dimensional, you can't imagine that, but that's what they're saying. Now, how do you explain this? This is what they call closed space. All right, let me give you a good way to understand it. I've got a telescope, a very nice telescope, and I used to take it out and look at the stars. And let's say that this is such a nice telescope. I've got a zoom handle on it where I can zoom it in, and look further and further out, just zoom it down even more and get further and further distant and so forth. And so I'm looking through this telescope one night and I keep cranking that zoom down, looking further and further and further, and pretty soon I can see, that's the back of somebody's head looking through a telescope. That's my head. So that's what they're saying, is that you just keep looking and eventually it comes back on itself, out there. And so that would be the closed space idea. And that makes your head hurt a little bit, but that's what they're trying to say. And all for the purpose of not wanting a center or any kind of special place to the Earth. Okay, so this is the Big Bang model of space and matter. Now, everything you see in gray out here doesn't exist because there's nothing outside. This is the initial, what do they call it, a singularity or whatever, the initial egg of the universe before it exploded. So all this matter is crammed down in this little egg right here, and then all of a sudden the Big Bang occurs. And you see it all expanding out like this. These are the galaxies now. And this is not an edge, this is space-time. Okay, this is all of space right here. So the space expands with the matter. Okay, there's nothing outside to the outside. It's just all, as it's expanding, new spaces being created at the same time. And so that's their explanation for this thing. There are other problems with the Big Bang model. Let's see. The Kobe space satellite back in the early 1980s, they sent that up. What they were looking for was this cosmic background radiation. Because if they figured if they could look far enough into the distance, billions and billions of light years away, they should eventually see, because you're looking back in time, right? They should eventually see the Big Bang. And so they should see evidence of the initial explosion of the Big Bang. And indeed, when they look out there, they see a bottom line temperature. The stars are hot, and so there's an average temperature of the universe. At the very furthest edges, the temperature is like 4 degrees Kelvin, which is 4 degrees above absolute zero. And so that's the cosmic background radiation. And so there's evidence that there was a Big Bang as far as they're concerned. But if you have an explosion, explosions don't make galaxies. You don't see spiral-shaped galaxies in explosions. I mean, if you explode up sand and so forth, it's just going to radially expand out from the center of the explosion. You're not going to get angular momentum spinning, solar systems and galaxies around and so forth and making all that kind of stuff. So they're looking for evidence that would be something in the early part of the universe that would explain this angular momentum in the galaxies they see. And so they imagined that they would see that out there. They really didn't. They claim they did, but it's so tiny and so small that it's just, anyway, that's a problem. So there's still problems with the Big Bang. Okay, continuing on in this book by Hawking and Ellis, they say, however, we're not able to make cosmological models without some admixture of ideology. You hear what he's saying? They got a preconceived notion they got to support, okay? We've got an ideology, a belief system that we've got to support. And so based upon that belief system, that's the way our model is going to turn out right there. That's Hawking and Ellis right there. All right, so what we're going to do, this theory that Russell Humphreys has right here, it's preliminary, it's not perfect, but it's pretty interesting. Starts with the Bible. It says, okay, let's use the Bible as our starting point. It's a pretty safe place to start, I would say. And it's going to make scientific sense, too. Now, okay, what's the consequences of there being no center and no edge to the universe? Then it means that if there's no center, then there's no center of gravity to the whole universe. Gravity is pulling equally on all sides, and so there's no force towards some sort of center. But if there is an edge to the galaxy, or to the universe, and if there is a center then, because if there's an edge, there must be a center, then there should be some sort of net gravitational force down to the center of that galaxy. Everything ought to be gravitationally connected in some sort of way in that. So that was Humphrey's idea here. He called it relativistic, well, he didn't call it this. This was Einstein's idea of relativistic time dilation. He's going to use this. So before, all right, I'm going to put this on hold because I got one more thing I got to explain to you. This is the toughest one. In 1888, two scientists named Michelson and Morley did an experiment. They figured that light had to travel through some sort of medium because it was like a wave, and they called it the ether, and they were looking for evidence of the ether, kind of like waves flowing through water. In order for a wave to go through water, it's got to have water, right? Well, in order for light waves to go through space, it's got to have some sort of ether, they called it. And so they were looking for evidence of the ether. So they were trying to build an experiment to test this for this evidence. And what they found out was that the speed of light is a constant independent of the relative velocity of the observer. Now that's a fancy statement. I'm going to have to explain it to you. This means that no matter where the light originated from, or no matter how fast you're going, you'll always measure the speed of light to be the same. Now, let's see if we can explain that. This Michelson and Morley's experiment was the most famous experiment that ever failed, because they were looking for light to move faster in one direction, in the direction of the ether wind, so to speak, and less fast to another direction. So they had a table that they had this, well, forget that. I think there's a diagram in there. If you want to look at that later, that's got how they used interference patterns to discover the speed of light and so forth. But anyway, the experiment failed. And they had this table where all this apparatus was set up, sitting on ball bearings, and they measured the speed of light with the table sitting this way, and then they rotated the table 90 degrees and measured the speed of light again, and it came out identically the same, even though the Earth's motion was, the rotation of the Earth was moving and so forth. And so they're trying to, this doesn't make sense. And that's when they discovered that the speed of light is a constant, independent of the relative velocity of the observer. Einstein took this idea and he came up with a thought experiment. And imagine a light clock. Now, a light clock of this sort has to be an imaginary experiment. He called it a Gedanken. That was German for thought experiment. And this light clock it's got a light bulb down at the bottom that shoots out a photon of light through a hole in a mirror, and the light goes up and strikes this mirror that's 1 light second away from the other mirror, and then comes back down. Now, how far does light travel in a second? 186,000 miles. So this is a real big clock. It's 186,000 miles tall, but it's a thought experiment. We can do this in our mind here. So when you run this light, and watch the beam of light go up, it's going to come out of this light bulb, hit the mirror, and come back down, and you can measure the length of time that it takes that light pulse to go up and come back down. And it should take 2 seconds. 1 second to go up, 1 second to come back down. So the elapsed time on this thing is 2 seconds. And what happens if you move this clock? Well, let's take another experiment. We're going to build a laboratory. Matter of fact, we're going to build a moving truck or a moving vehicle of some sort. And we're going to put this light clock inside this moving vehicle, kind of like a panel truck, but it's going to be real tall, okay? And we're going to have this truck move at the speed of 1/2 the speed of light, 1/2 speed of C, okay? And so as this, now watch this light flash, it'll go up, and we've already seen this one. But from, you got 2 observers. This guy's standing inside the truck, and this guy has his twin. He's standing outside on the ground watching this truck move by. So this guy down here is stationary. This guy up here is moving, and they're both going to measure the same event. This event is going to happen, and for this guy, he's going to measure it going up and down in 2 seconds. This guy's going to see the truck moving, and so he's going to observe this light having to go on this angle, because it starts out here, the truck's moving, it's going to hit the mirror about halfway through, and as the truck keeps moving, it's going to come down and hit the other one. So the light is going to move a further distance because it's got to go at an angle up to the mirror and then an angle back down to hit the bottom mirror. So from his perspective, the light travels a further distance. From this guy's perspective, the light travels only a single light second. And it turns out that the time it takes to go up and down is 1.3 light seconds to go up and 1.3 light seconds to go down, because that's the distance of the light here. And so the total elapsed time is 2.6 seconds. Here it is. Watch the light. Boom, boom. So you see the light pulse takes longer when this guy measures it than it does when this guy measures it down here. Now, since light is a constant independent of the relative velocity of the observer, this guy's clock has to slow down in order for him, compared to this guy's clock, in order for them to get the right answer. This guy's got to measure the same event happening in 2 seconds, whereas this guy's got to measure that same event happening in 2.6 seconds down here. Now, that's kind of mind-bending, but the only way, because they haven't changed the distance, both of them are measuring the exact same event, so nothing's changed on that. The only thing that can change is time. So this guy's clock has got to elapse 2 seconds, while this guy's clock elapses 2.6 seconds. Same event down there. So, kind of crazy, but that's indeed what happens and has been demonstrated experimentally many, many times at this point. Now, if clocks, now you've heard about, surely you've heard that on science fiction stories and so forth, where you got two brothers, two twins, whatever, and one of them gets in a spaceship and travels to Alpha Centauri. He's gone for 8 years and then he comes back. For him, it was an 8-year trip. But the guy, his brother on Earth, aged 40 years in that same period of time. You've heard of that's all relativistic time dilation, and it's due to motion. The spaceship going out and coming back is motion out there, and so the clock slows down because of that motion. This traveling twin, its clock slows down. Now, how do we make this work for gravity? Because the theory behind this book, Starlight and Time, is that time slows down because of gravity as well, which is another outcome of Einstein's special theory of relativity and general theory of relativity. Time dilation due to centrifugal force, not due to motion. Okay, so let's watch this. Think of this as a merry-go-round. Okay, we're looking at the top of a merry-go-round, and I've got 3 clocks. I've got one clock sitting right on the edge of this merry-go-round, and I've got one clock right here at the center of this merry-go-round, and I've got another clock sitting outside the merry-go-round. And so there's 3 clocks: center clock, edge clock, and outside clock. Okay, that's the way I'll speak of them. And so if I start spinning this disc or this merry-go-round, you're going to observe that the edge clock moves relative to this outside clock over here. Now, because he's moving, we've already shown that motion causes your clock to slow down. This edge clock is now going to be running slower, at least while it's moving, versus this outside clock, because he moved relative to that. And so there's a difference in time here due to the velocity, okay, due to the relative motion of this edge clock right here. So the edge clock runs slow, the outside clock runs normally. Now, but what about this center clock? Did its time change over here? Did it go anywhere? It didn't go anywhere. So it didn't move relative here. And as a matter of fact, indeed, it just runs normally. So these 2 clocks run normally. The edge clock and the outside clock. The center clock and the outside clock run normally out here. But why is there a difference between the center clock and the edge clock? Because forget the outside clock, throw it out of the picture. These 2 clocks don't change relative to one another. I mean, basically, they stay exactly the same distance apart relative to one another in their frame of reference. You've sat on a merry-go-round before. You and your buddy or your wife or girlfriend or whatever riding on 2 different horses over here, and you're going up and down, and when you look over at her, she doesn't change relative to you, okay? And vice versa. When you look at the center of that merry-go-round, it stays the same distance from you the whole time. The rest of the world travels around. Matter of fact, this is the way it looks when the rest of the world goes. You and your buddy, or you in the center here, stay what appears to be in sync with each other while the rest of the world spins around you on that merry-go-round. And so why is there a difference between this clock, which is running slow, and this clock? The only difference between these two things is something this edge clock feels. You're sitting on the edge of this disc and you're going around. What do you feel? It's trying to do what? The centrifugal force is trying to throw you off, right? Now, the person in the middle doesn't feel that, right? But the person on the outside, this edge right here, this edge clock is going to feel that centrifugal force. And so that's the only difference between the edge clock and the center clock is the centrifugal force. And so that is the only reason for there being a difference in clock speeds is due to the centrifugal force right there. Now, centrifugal force then is equivalent to acceleration. Acceleration and centrifugal force have the same fundamental effect. Here, let's explain it like this. This was another Einstein experiment. He imagined a spaceship accelerating in space. Now, I mean, if my spaceship is just sitting out there floating in space, I've got a basketball inside this spaceship, and the basketball is just kind of float around, weightless, right? But what happens if I fire those engines? Okay, if I fire those engines, that basketball then is going to start falling down towards the ground because I'm accelerating, okay? It feels just like centrifugal force. I mean, it's the same kind of feeling right there. Now, what's the difference between that and the spaceship sitting on the Earth? The basketball falls down here too. If you're inside these spaceships, no windows, no doors, no anything, you can't look out, do you know whether you're standing on the Earth or whether you're just simply accelerating in space? You can't tell the difference. They're equivalent to one another. So, follow me on this. We know motion slows time. We know that centrifugal force slows time. We saw that on the disk. Centrifugal force is equal to acceleration. Acceleration is equivalent to gravity. Therefore, gravity slows time. That was the logical process right there that Einstein came up with. And he demonstrated this over and over again through some, he made some predictions as to how this would happen. And indeed, they came out. This has been shown by experiment. There is a clock, an atomic cesium atom clock in Boulder, Colorado, that is now our national standard for time measurement. Okay, it's our second is defined by this clock in Boulder, this atomic clock in Boulder, Colorado. It's accurate to within 1 microsecond a year. That's 1/1,000,000th of a second. Take a second, divide it into 1,000,000 pieces, and that's how accurate this is. It only loses or gains 1 microsecond in a year's period of time. But it's up in Boulder, Colorado. There's another atomic clock in Greenwich, England. Okay, identical clock. You could swap these two clocks, and they would run identically in the same place right here. But the Boulder, Colorado clock is at a higher elevation than the one at Greenwich. Greenwich, England is like what, sea level, just a few feet above sea level. Boulder, Colorado is not many feet lower than Denver, Mile High City, so it's somewhere in the neighborhood of 5,000 feet above sea level. Now, gravity, as you get further away from the center of the Earth, gravity drops off, right? And so you have less gravity up on top of this mountain than you do down at sea level. You go deeper into the Earth, the gravity gets stronger as you go deeper if you drill a hole into the Earth right there. And so if gravity slows time, then lower clocks tick slower than higher clocks. So that's a good reason for living in Memphis, Tennessee, as opposed to some mountain somewhere. Because you're not going to age as fast, right? Now, it's not a lot of difference right there. But this has actually been demonstrated. Matter of fact, the clock in Greenwich, England, clicks 5 microseconds slower than the clock in Boulder, Colorado, and it is exactly fits with the calculations that you would expect for gravitational time dilation. You could swap those two clocks, and then the other clock would then tick 5 seconds slower because of that gravitational difference right there. And so, Russell Humphreys, he has this concept called white hole cosmology. Now let's see if I can finish this up here in the next 5 minutes. He says that clocks tick differently in different parts of the universe. Clocks run at different rates in different places in the universe. And as I said, he starts with the Bible, and he says in the Bible that in the Genesis 1:1, in the beginning God created the heavens and the earth. And so he started with the earth. The earth is the center of everything, because it wasn't until day 4 that he put the sun, moon, and stars out there, right? All that stuff. And we'll see how this is going to, in his cosmology, there is a center and an edge of the universe, because in the beginning God created the heavens. What's that? That's not the sun, moon, and stars, because those didn't come until day 4. And it's not a summary verse. That's the space that God created, the heavens and the earth. That's all matter, space, and time. In the beginning, time, God created the heavens, space, and the earth, matter. Everything, all of the universe, right there. And so he's got all the matter that's going to take for the universe sitting in this central spot right here. He said the earth was formless and void, remember? So he's got this big pile of unformed matter and so forth. And there's some verses in Isaiah. For example, Isaiah 40, verse 22 says, God stretches out the heavens like a curtain and spreads them out like a tent to dwell in. 42:5 says, for who created the heavens and stretched them out? 44:24, who stretches out the heavens all alone? 51:13, who stretched out the heavens? Job 9:8 says, he alone spreads out the heavens. 37:18, with him you have spread out the skies. That gives you the idea of spreading out space, doesn't it? I mean, God is making space out here. 104:2, Psalm 104:2, who stretches out the heavens like a curtain. Jeremiah 10:12, and has stretched out the heavens at his discretion. Zechariah, there's 40 different verses in the Bible. Is that right? Yeah, 40 different verses in the Bible that speak to stretching out the heavens like this. It's either 40 or 17, I can't remember, but it's more than what I've got up here. Zechariah 12:1, thus says the Lord who stretches out the heavens. And so there's evidence that God stretched out the heavens right here. So you remember that model of the Big Bang, where they said that because of the cosmological principle or the Copernican principle, that there is no edge and there is no center, and that space is created along with the matter stretching out like that during the Big Bang. Well, according to Russell Humphrey's model here, God stretches out empty space to begin with. Okay, so there is the empty space, and right there at that little green dot is all the matter, okay, sitting there. So God creates the heavens, all these things, and the earth right here in the beginning. And what was the matter? Well, he calls it water. You know, God said the whole face of the earth was covered with water, okay, and with the waters, and the Spirit hovered over the face of the deep. And notice, by the way, that there is an edge in this model and a center. And since all this matter is jammed up into this center, it's going to be very heavy gravitational pull in the center of that, okay? What happens to clocks when they're in the center of gravity? They run slower. So there's a difference between how fast this clock runs right here and how fast this clock out here is going to run. And so God separated the waters above and below. If the waters were the original matter, he's going to take that water, he's going to spread it out. You know, hydrogen is mostly what stars are made of, so H2O. It uses that oxygen to ignite those stars and so forth, so he creates the stars with water. That's the basic elements that he's using out there. And he separates that, and so watch what happens here when he creates all the stars on day 4, the sun, moon, and stars on day 4. So here you've got all this stuff right here. So because it's so heavy, now you may not have heard this term before, but there is something, well, maybe you have, if you've heard of a black hole. You ever heard of a black hole? Okay. A black hole sucks all matter into it, right? I mean, if you get close to a black hole, you get sucked in and you never can get out. Light can't even escape from a black hole. And they say that there is a point at which you get close enough to a black hole, there is no return. You can't get out from there. It's the event horizon, they call that. Well, this would be just like a black hole here. It's so heavy, so gravitationally powerful right here. There would be an event horizon in this particular black hole right here. So there is the event horizon. All the sun, moon, and stars, and the earth, and matter, and so forth, the waters, and so forth, are inside the event horizon. Everything inside the event horizon. Time runs real slow inside there, almost stopped. So God places all the matter in here, and then He spreads them out. It's called a white hole instead of a black hole. A black hole, everything sucks in. A white hole, which Stephen Hawking predicted in his book, white holes, if they exist, would spew matter out. And so watch the matter being spewed out of this white hole. Now watch the event horizon at the same time too. The event horizon, as the matter gets spewed out, is going to start to shrink because the gravity is going to be less and less and less as that matter gets all spread out. And so what you're seeing here, these are all the galaxies out here, and the event horizon eventually goes away. What's left is the Earth right here in the center of the solar system, or our galaxy or whatever is right here in the center. And so there we are, still in the center of the universe like that. Now, what happens while all that stuff's happening? Inside the time, billions of years of time can pass for those galaxies that are out here. Oh, I'm sorry, for those galaxies that are outside, and on where the Earth is inside that event horizon for those first few days, your clock will be running normal 24-hour days for 6 days. And so relativity, because of the gravitational time dilation, predicts that the formulas, you can take the relativistic formulas and take the different assumptions, the assumptions we get starting with the Bible, and crank this thing out and come up with that different the different assumption. It's 7:33. We need to stop, but let me finish by saying this. God defines a day in verse 5. He says, God called the light day, and the darkness He called night. So the evening and morning were the first day. If someone were to ask you how old is the universe, what you should say is by whose clock? Earth Central Time or GST? No, GCT. God Central Time or God Standard Time, God GST, Galaxy Standard Time, whatever you want to call it right here. So by whose clock? How old is the universe? So it's preliminary. It needs some more work. These are the same guys that have been working on that rate project I told you about last week. At least Russell Humphreys is on that team. And so perhaps more progress will be made on that. The point is, don't place your faith in any particular theory. I don't know how God did it, but I know I would hate to say and stand in front of the Creator of the universe when I meet Him in heaven and say, Lord, I couldn't figure out your very plain word of 6 days. And so because I couldn't figure it out with my pea-sized intelligence, I assumed that it was over, all these other billions of years and so forth. And He's going to say, well, guess what? That's the way I did it. And so I don't know what He'll say, but we'll know Him as He is one day. Okay, let's pray. Father in heaven, I pray that we might be comforted by Your word, Father, because we can trust Your word. And so, Father, I just ask that You'd help us to understand, even with our limited knowledge and intelligence, Father, and give us glimpses of the magnificence of Your creation, but also the magnificence of what Your Son did on the cross 2,000 years ago in dying for us. He was nailed to that wooden cross, Father, but He made the wood that cross was made out of. And I just praise You for that He died for our sins. Go with us now to our homes. In Jesus' name, amen.